Okay, we're going to look at some applications of dot and cross product. First application we're going to look at is work. Work is defined as force times displacement. Okay, and the force is a vector, as we know, and it's measured in newtons for its magnitude. It also has a direction. Displacement we're going to call S, and it's measured in meters. So that work will be measured in joules, and 1 joule is a newton meter. Okay, so an example. Well, we've got a lawnmower, okay, and let's say that the force down the handle of the lawnmower is 200 newtons. And the lawnmower moves 12 meters. So if the force down the handle is 200 newtons and it moves 12 meters, let's see how much work is done as defined by this formula. Okay, so we're also going to say that the handle is at 40 degrees to the horizontal. Now it's the horizontal force, or the component of the force, that is really going to be achieving some work on this lawnmower. The vertical component of this force, the component down, is actually going to achieve no work because the ground is going to force back up with the same force and it will be in equilibrium. Okay, so we really need to look at the horizontal component. Now we look at the formula. Okay, so work is force dot displacement. Well, we put that in and we got force, magnitude of force, times magnitude of displacement, times cos theta. Okay, so the formula magnitude of F times magnitude of S cos 40 is just the dot product. But magnitude of F cos 40 is really just the horizontal component of this force. And we're reducing this down to a one-dimensional problem, and we're looking at as if somebody was pushing the lawnmower directly in the direction that it's going. Okay? And so the work that's been achieved on this is going to be 1,838.51 newtons when you multiply this all out. Joules when you multiply this all out. Okay, so that's how that one's going to work. Now another way of looking at this is by looking at it as if everything was given in coordinates. Okay, so here is a possible question that could be asked. I'm not going to solve it completely. I'm just going to set it up mostly. So imagine that you have a force that is 25 newtons, okay, and it's acting in the direction of this vector v here, which is 2, -1, 3. Okay, so it's acting in that direction. Well, the force has to have a magnitude of 25 newtons, and if you calculated the magnitude of this vector here, it's not going to be 1. So you can't just say that the force vector is 25 times this vector here. Okay, what you need to do is write F in coordinate form so that F equals 25 times v hat. V hat is the unit vector in the direction of v, and it has this formula. Okay, so that will give you the force vector, 25 times v hat, and you'd have to work that out. So you need to work out what v hat is, or the magnitude of v is, to get that. Okay, now let's say that so that's the force that's being applied. Now we have a force vector. What about its direction? Well, if direction was given in terms of points in, say, a 3D system, so for S, the displacement vector, the object moves from A to B. Well, then you'd have to find the vector AB, and that would be the S vector. And then we'd have the work. We could say that the work is force dot AB. So the force as we've defined, and AB you'd have to find as OB minus OA. Okay, so I'll let you work out that problem. Okay, another example of, this one is an example of cross product. An application of cross product torque. So torque is defined as R cross F. Okay, so R cross F, what we have is the radius from some axis of rotation and where a force is being applied. Okay, so imagine that you have a door. Okay, so a door is on a hinge right here, and the door goes out like this, and then somebody is pushing on the door right here. Okay, and the door opens that way. Or somebody could be pushing on the door right here, and the door would still open that way, but if they're applying, I hope you can imagine this, if they're applying a force here that's equal to that force, it's going to be harder to open that door here. So if they're applying the force here, it's going to be easier to open the door, and you're going to achieve more torque. Okay? If you increase the force, you're going to achieve more torque. If you increase the radius, the distance from the axis of rotation, you're going to receive more, you're going to get more torque. Okay, so the magnitude of the torque is magnitude of r cross F. Okay, also torque is a vector, so imagine if this hinge here was instead a bolt and this was a wrench. So if you turn the wrench, then the bolt is going to move in a direction that is perpendicular to the force and the radius. The bolt is going to go down. Okay? So that works with the right-hand coordinate system if the bolt is right-hand threaded. Okay, so that's how torque works. So the radius, or the force is in newtons, the radius is in meters, and the magnitude of the torque is in joules again. Okay, so newtons, meters. So imagine we have this problem. Okay, Michaela applies a force of 30 newtons to the end of a door that is 60 centimeters wide. The force that she applies is at 80 degrees to the door. Okay, so the door, she's not pushing directly at the door like this. She's pushing at 80 degrees to the door, like that. Okay, so she's not achieving the maximum amount of force that she could on that door. Okay, determine the magnitude of the torque. So here's the solution. Okay, so here's the setup. Basically, if she's pushing like this at 80 degrees, 60 centimeters is the magnitude of the r vector, and the force vector goes like this. So really what you're looking at is the component of that force vector that is perpendicular to the door. And how you get that is going to be the magnitude of the force times sine of 80, which happens to work out to the cross product when you multiply it by r. Okay, so this is the formula for this problem. So magnitude of r times F, 0.6, don't forget to change the centimeters to meters. Okay, 30 newtons, sine of 80 degrees gives you 17.73 joules. If the problem were to be in coordinate form, so say you have, so this is another possible question, rotating object fixed at some point A, so this is going to be where the axis of rotation is, or point of rotation, applying a force to a point that is at B, okay, this point here, -321, with a force of, magnitude of the force is 25 newtons, okay, in the direction of V. So this is the same V as the previous possible question on work. Okay, so it's heading in the direction of this. Well, again, then we need to then find the force vector. So it's going to be 25 newtons times the unit vector V. Okay, so there's the force vector, and then the radial vector. Okay, so that's the radial vector, not S, and it will be AB. Okay, so AB is the radial vector. Okay, and then the torque, the magnitude of the torque, will then be r cross F magnitude, which is going to be AB cross 25 V hat. And you can work out those, and you should be able to get the torque for that problem. Okay, and then the last of the applications, there are other applications, but these are the ones we're looking at. Volume of a parallelepiped. Well, here's my drawing of a parallelepiped. Okay, the volume of a parallelepiped is the area of the base times its height. we know how to find the area of the base. The area of the base is the magnitude of the cross product of the two vectors. Okay, the volume is going to be that area times the height. So the area of the base is the magnitude of the cross product. The height is going to be this vector c projected onto something perpendicular to the base. Well, it's convenient that we can figure that out. Something perpendicular to the base is going to be a cross b. So if I take c, vector c, and I project it onto a cross b, I'm going to get a vector that's equal to the height. Now, a projection can be positive or negative. We want the positive, so we're going to say that the height is the absolute value, because h needs to be greater than 0, absolute value of the scalar projection of c onto a cross b. C projected onto a cross b. Okay? And when we look at that, well, this is absolute value still. That formula, as we can remember from before, is c dot this vector divided by the magnitude of that vector. Okay, so you have to look back at the formulas for that, and you'll see that's what it is. And if we plug this all into the volume equals the area of the base times the height. So the area of the base was a cross b, magnitude. The height was this formula here. Plug it in. And a cross b cancels out. And we get this nice formula here where these lines mean absolute value. Okay? So you do the cross product first of a cross b and dot it with c, and then you get the volume of the parallelepiped, called the triple scalar product. Okay? So you want to try this with some numbers, so you can check it with these numbers here and see what you get. So here's an actual example to do. Okay, and that's it for these applications. Other applications would involve maybe finding the area of a triangle. Okay, so if we go back up here and we look at this, if we put a line across here, we would have a triangle. If you want to find the area of that triangle, well, you find the area of the parallelogram and divide it by 2. Okay, so that's another application.